Hello everybody. We continue, and today's first section is 17.1, continuity of the inverse function. Let me recall that we formulated theorem. In fact, it was in section 16.2, and this theorem says that if f is continuous and strictly monotone on an interval I, then f minus 1, the inverse function, is strictly monotone and continuous on f of I. F of I is also an interval, and we proved that f of I is an interval and that the inverse function is strictly monotone. So during last lecture, those two things, and this is an interval, was proved during former lecture. So now we have to prove continuity. That is the question. So, proof of continuity. So, today we continue the proof of that theorem. And, okay, what we have to prove? So, we want to prove that if y naught is in f of I, then the inverse function is continuous at y naught. That is what we want to prove, right? That is what we need to prove. And by contradiction, let f minus 1 be not continuous or be discontinuous at y naught. What it means? It means, hence, there exists a sequence yn, and from 1 to infinity in the image, such that the limit of yn equals to y naught, but the limit of f minus 1 of yn is not equal to f minus 1 of y naught. That is what is contradiction? So we suppose that the inverse function is discontinuous, so by Heine definition is not fulfilled, and it means there exists a sequence yn in the domain of the inverse function, and the domain is f of I, such that yn tends to y0, but the values of the inverse function do not converge to the value of the inverse function at the point y0. That is what we need to prove. Okay, so let us write down what means the limit is not equal to f minus 1 of y0. So we don't care about the existence, so we don't know if the limit exists or not. But in any case, either the limit doesn't exist, or the limit exists but it's different from f minus 1 of y0. So we can write down the definition of the limit of the sequence and to take its converse. So what it means? We deduce from this relation that there exists epsilon greater than 0, such that for arbitrary natural number n, there exists n greater than capital N, such that the values of f minus 1 of yn are satisfied to the inequality greater or equal to epsilon. So that is the definition of this relation, right? So we take definition of the limit and take opposite assertion. Okay, again, so let me denote just by epsilon naught this epsilon which exists, right? And here it is written for arbitrary capital N, so it means what we can do. So firstly, let's choose n equals to 1, right? Then there exists n, and I'll denote it by n1, where n1 is greater than 1, such that we have the inequality f minus 1 of yn1 minus f minus 1 of y0 is greater or equal than epsilon naught. And we continue to proceed in that way. So it means next capital N will take this n1. So there exists n equals to n2 will denote this, which is greater than n1. So f minus 1 of yn2 minus f minus 1 of y0 is greater or equal than epsilon naught. And so on. So we can construct the sequence nk minus 1. There exists n equals to nk greater than nk minus 1, such that f minus 1 of ynk minus f minus 1 of y0 is greater or equal epsilon naught. Okay, and so it means that we have constructed the sequence, or better to say, this subsequence of our sequence f minus 1 of yn such that for all k in n we have inequality f minus 1 of yn k minus f minus 1 of y naught is greater or equal than epsilon naught. Okay. So, where are values of those function or of the function f minus 1? Definitely they belong to our interval I. So, in fact, they exist unique for every k in a natural. They exist unique x and k, I will denote it, in I such that x, or maybe xk, let it be xk, right? Xk equals to f minus 1 of y and k. So, we know that the function is strictly monotone, hence it is 1 to 1. It gives an 1 to 1 correspondence between the intervals I and f of I. So there exists a sequence, xk, k from 1 to infinity, which is in the interval I, Okay, in fact, I should put here extra supposition about boundedness of the interval I. So, let us put extra supposition. So, suppose I is bounded. So we have a bounded interval, right? Then, by Boltzanoverstrasse theorem, theorem, right? In fact, here I should put another s, doesn't matter. So, by Boltzanoverstrasse theorem, there exists subsequence k l xkl l from 1 to infinity, such that xkl converges, limit as L tends to infinity of xkl equals to, let's say, x naught. Okay, what can we say about this x naught? In fact, I should put extra supposition. Let me is bounded and closed, right? That is better, firstly. It means I is just a segment, AB. So, then, if we suppose I is bounded and closed, then X naught belongs to I, right? So, what we know that the function f is continuous at x naught. So, what it means, the function f is continuous at x naught. So, then what it means, what it gives to us. The function f is continuous at x naught. We have a sequence xkl, which is definitely in our interval I. Hence, by the Heine definition, hence the limit as k tends to infinity of f x and k, L tends to infinity x k L equals to f of x naught. Now, f of x k L, what is it? We know that x k L is f minus 1 of y n k L. So I should substitute instead of k L here. Hence, y n k L is the value of x k L. So I can rewrite it as limit of the sequence y n k L equals to f of x naught, f of x naught. But we supposed that, oh, I erased it, sorry. Limit of yn equals to y naught. This was at the beginning of the proof. Limit of yn equals to y naught. Hence, y naught equals to f of x naught, right? Because ynkl is a subsequence of yn, and yn converges, hence arbitrary subsequence of the convergent sequence yn converges to the same limit, y naught. Hence we have y naught equals to f of x naught. Okay. Then, what it means, so y naught is f of x naught, so it means that x naught equals to the value of the inverse function at y naught. So now let us write down what we supposed. So we supposed the limit as L tends to infinity of xkl equals to x naught, right? Now that is the same as limit as L tends to infinity. xkl is f minus 1 of y n kl, right? And this is equal to x naught is f minus 1 of y naught. But we know that for arbitrary k, that is how we construct it, right? I will not rewrite it. Just refer to this inequality, which is still here, right? So for arbitrary k, f minus 1 of y and k cannot approach to f minus 1 of y naught. There is a positive epsilon naught between, distance in positive epsilon naught between. Right? So we have a contradiction, and it means our theorem is proved. Theorem is proved for I bounded and closed. So bounded and closed interval is a segment, right? Okay, now let us consider what happens, for example, so suppose I is bounded, nothing else, right? For example, I is an interval which is not closed and not open, right? So just from one side. Then, by the first part, in fact, the first part, I mean, what we proved last time. By the first part of the proof, we know that f of I is an interval with ends infimum f of x for x in I and supremum f of x, right? So if f is increasing, then infimum f of x equals to f of a. Since the function is continuous at a, so if so it just how to prove it, right? So let us prove it. Indeed. So suppose infimum is less than f of a, right? Then what it means? It means that f of a is not a lower bound for the values of f of x. So there exists x not in I such that f of x naught is strictly less than f of a. And that is a contradiction, because x naught is in I means x naught is greater or equal than a. And it's impossible for an increasing function. And analogously, you can proceed even easier, that infimum of f of x cannot be greater than f of a, because f of a belongs to the set of f of x, right? So other strict inequality is impossible just by definition of the lower bound, in fact. So infimum is a lower bound. That's all. Okay. So what is about supremum? What is about supremum? There are two possibilities. So supremum, in principle, supremum is less or equal than plus infinity, right? So it may be equal to infinity. That's what is a difficulty, right? So if look, if supremum for x in I, f of x, is less than infinity, then limit as x tends to b minus f of x equals to this supremum. Right? Because the function is monotone, hence it has a limit for sure. And this limit cannot be different from this supremum. It is proved just analogously. So, and we can define f tilde of x like that. F of x in semi-interval, and this limit for x equals to b. Then f tilde is strictly increasing and continuous on closed interval AB. Hence, the inverse function is continuous on f tilde of the closed interval. And that is precisely the interval f tilde of A, f tilde of B, or f of A limit as x tends to b minus of f of x. That is where the inverse function f tilde is defined and continues by what we have proved. And we can see that f tilde minus 1 of y equals to f minus 1 of y for all y in the semi-interval f of a, limit as x tends to b minus f of x, and here I'll not include this limit. So, since f tilde is continuous at every point of this closed interval, then f minus 1 is continuous on this part of that closed interval. So, we have proved our result for the case when supremum is strictly less than infinity, right? Then, what happens if supremum if supremum for x in I, f of x is equal to infinity, right? Then what it means? Then f of I is precisely infinite why you should find everything in lecture notes. That is slightly different, yes, you are right. In fact, in your lecture notes, theorem was given just for the case of closed interval, nothing else. Yeah, so, yes, theorem 4.8.4 is precisely for closed interval, nothing else, right? So, theorem 4.8.4 was proved at that moment, right? That is the end of the proof. Then, there is a remark, 4.8.1, which says a similar result holds is the open interval. Interval with some additional considerations, right? And these are just those additional considerations. So, I gave you more general result for arbitrary interval, not only for bounded closed, but for arbitrary. And now I am giving you all details of those additional considerations. So, okay. So what we do now, so if here we have infinity, then we have such an image, right? And what we want to prove? We want to prove that f minus 1 is continuous at arbitrary point y naught, let's say, in our infinite half line, infinite ray, right? So, okay, then I can proceed as follows. Look, f minus 1 of y naught, let us denote it by x naught. It belongs to the interval a, b, such interval, right? And now we can proceed as follows. So, let us also consider f minus 1 of y naught plus 1, let's say, right? And denote it by, let's say, C. C is also in AB, and because of strictly increasing of the function f, for sure x naught is less than C, right? Because f minus 1 is also strictly increasing. Yeah. So now what we have, we can consider f on the interval AC, right? That is strictly increasing and continuous function. Hence, by the proven part, f minus 1 is continuous on f of this interval, and that interval is precisely f of A, and f of C is y naught plus 1. Hence, f minus 1 is continuous at y naught. So, we wanted to prove that f minus 1 is continuous at arbitrary point of our infinite interval, and we have proved it, right? So it means now we completed the proof for the case I is bounded. For the case of bounded interval, the proof is completed, right? And finally, we can consider the case of infinite. So, suppose now suppose I is unbounded. Okay, let us say this is from A to infinity, let's say, right? Say right? Unbounded, say A infinity. Then again, f of I is f of A, and that is a claim, limit as x tends to infinity, f of x. Why? Why? Because this limit exists for sure, either finite or infinite, we don't know. If it is finite, then we have proved that the image is an interval, and so we need to prove that this limit cannot be a value of f at a point of I, and this can be done analogously to what we did before, right? So, but you need to prove it, right? So that this limit which exists, even if it is finite, then it cannot be attained by the function f at arbitrary point of this half line, right? Okay. Okay, let's have a break. So the only thing which we need to prove here is that this limit is not attained by the function f, and it can be proved analogously, right? So then once again everything is repeated what we did before, right? So that's the end of the full proof, right? So what I did, I have proved even more than is said in remark 4.81 together with theorem 4.8. Yeah. Of course, for strictly decreasing function, everything is analogously, and so okay, that's all for this section. Maybe a couple of examples to apply the theorem. So, examples. Sine -1 is continuous on, so usually, we take it on -1 and proof, consider y equals to sine x on minus pi over 2 pi over 2. That is continuous function as we know, and it is strictly increasing on that interval, what can be proved easily by, so x1 less than x2, right? Then sine x1 x2 minus sine x1 equals to 2 sine x2 minus x1 over 2 times cosine x1 plus x2 over 2. So what we know about x1 plus x2? x1 plus x2 over 2 is somewhere between minus pi over 2 and pi over 2, since both x1 and x2 are somewhere here, right? And okay, maybe I should write it here, otherwise, yeah. So this says that cosine x1 plus x2 over 2 is non-negative, and in fact it is strictly positive. Why? Because here in fact we can insert this is a strict inequality, since at least one of those x1 or x2 they cannot be equal, this expression cannot be equal to pi over 2, because x2 may be equal to pi over 2, but x1 is strictly less than x2, hence this is strictly between, right? So this cosine is strictly positive, and x2 minus x1 over 2 is, so if both are here, then difference between them is from 0 to pi, and we divide by 2, so this is between pi over 2 and 0. Hence sine is positive as well, is positive. So it means that is a positive expression, and it means sign is increasing. It is increasing, strictly increasing, strictly increasing, strictly increasing, and continues on this interval, right? So there is an inverse function, sine minus 1, which is continuous and strictly increasing as well, right? Okay, also sine minus 1x, sometimes it is denoted by arc sine. It's the same. And other examples of inverse trigonometric functions. So cosine minus 1 is continuous on minus 1, 1 as well. And here we should consider cosine x on 0 pi. 0 pi. It is also continuous, but decreasing, strictly decreasing on that interval. Third, tan minus 1 is continuous on minus infinity, infinity. Here we should consider y equals to tan x on interval minus pi over 2, pi over 2. And, okay, obviously, cotan minus 1 is continuous on minus infinity, infinity. If we consider y equals to cotan x on 0 pi. 0 pi. That is about continuity of inverse trigonometric functions. And you see that we consider to both cases, open interval and closed interval as well. Okay. So, next section is about uniform continuity, and it is a rather long section in your lecture notes. Hence, I'll split it into two parts. So, today we'll consider just the definition. So 17.2 is definition of uniform continuity. So, definition. F is called uniformly continuous on X in R if for arbitrary epsilon greater than 0 there exists delta greater than 0 such that for all x1, x2 in X satisfying the inequality x1 minus x2 less than delta, we have the inequality f of x1 minus f of x2 less than epsilon. So, let us discuss this definition. Let me compare it with, compare with continuity on X. So what means f is just continuous? So let us forget for a while about the word uniformly. What it means then? So what is continuity? F is continuous on X if it is continuous at arbitrary point of X. And this is the same as to say that for arbitrary x1 and x, and for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x2 in X, which satisfies this inequality, we have f of x1 minus f of x2 less than epsilon. So, that is just the definition of continuity at arbitrary point of capital X. Compare those two definitions. You see that the difference is in the place of this quantifier. So here delta depends on the point where we consider continuity and on epsilon. But for the uniform convergence, delta depends only. Delta depends on epsilon only. Right? And that is the difference, in fact. Once again, maybe some geometric intuition. So look, what means continuous, right? Continuity at a point means, so if we have continuous function at a point, take this point, okay, let it be x1, right? And we want to prove that it is continuous. It means that once we choose epsilon, so that is epsilon, and once we choose an interval on the y-axis, we can find delta, let's say this one, delta, such that for all values in this delta neighborhood, the values, right? The values will be inside our epsilon neighborhood of f of x1. In other words, we construct a rectangle. So once again, for arbitrary height of this rectangle, we can find width in such a way that, you see, the graph of our function is precisely inside this rectangle, and it intersects the left and right sides of the rectangle, not the top and bottom, no. So you can always find such a rectangle that the graph enters to this rectangle from the left and leaves from the right. That is continuity, right? And uniform continuity means that once you choose epsilon, you can find a delta in such a way that you can move this rectangle along the whole graph, and this property will be valid everywhere. So it means that, roughly speaking, the graph cannot, let's say, oscillate too much. That's some kind of intuition behind this definition. Okay, what are properties of uniformly continuous functions? Let me give maybe some examples. I will start with some examples. Yeah. Okay. So, what is not continuous, right? Negation of this definition. Negation, so, can be written down immediately, just by logical considerations. So, f is not uniformly continuous on X. What it means? If and only if it follows directly from the definition that there exists epsilon greater than 0, such that for all delta greater than 0, we can find x1 and x2 in X, which are located closely to each other, namely less than delta, and such that the opposite inequality is true, greater or equal than epsilon. That is what we can deduce from the definition immediately, right? F is not uniformly continuous if and only if this is true. Okay, some yeah, in fact, there is a theorem, right? A little bit very easy theorem. Theorem 1, if f is continuous, is uniformly continuous on X, then f is continuous on X. That follows from the definition immediately, right? Because, yeah, you should find delta which depends on x1 and epsilon, but if we can find delta which does not depend on x1, even better, that's all. So, examples. Examples. 1. Constant function, right? Constant function. In fact, doesn't matter where it is defined. F from D to R, f of x equals to c. Why it is uniformly continuous? Is uniformly continuous. On D. Why? Because here the inequality f of x1 minus f of x2 less than epsilon is satisfied for arbitrary delta, in fact, right? Because this difference is always 0. Hence, for arbitrary epsilon, we can take arbitrary delta. And that's, in fact, the unique situation when we can choose arbitrary delta. Okay, second example. F of x equals to 7x minus 2 is uniformly continuous on the whole real line. Why? Okay, just consider, okay, what I need to prove this chain of quantifiers from the definition, right? So let's look at the difference f of x1 minus f of x2. There is 7x1 minus 2 minus 7x2 minus 2. That is 7 times x1 minus x2. So the modulus f of x1 minus f of x2 is equal to 7 times modulus x1 minus x2, and it will be less than epsilon for all x1, x2, such that x1 minus x2 less than epsilon over 7, right? Because if this is less than epsilon over 7, then definitely 7 times this modulus is less than epsilon. So this will be taken as delta. So we can choose delta equals to epsilon over 7. Okay. Okay. There are more examples of uniformly continuous functions. Yeah, let me give a couple of results. One of them will be positive, another negative. So Theorem 1. Firstly, definition, sorry. Definition 2 for that section. Here, definition 1. F is Herder continuous. Herder continuous on an interval I if alpha from 0 up to 1 and m positive, such that for all x1, x2 in I, f of x1 minus f of x2 is less or equal capital M times x1 minus x2 power alpha. Okay, so and also for alpha equals to 1, f is called f is Herder continuous. Herder continuous. Also, is same as to say f is Lipschitz. Continuous. If I don't correct Lipschitz. Yes, not, sorry, Lipschitz continuous, yeah, okay. Yeah. In fact, there is very good condition for Lipschitz continuity, but it's too early to give it. Theorem 1. If f is Herder continuous, on I, then f is uniformly continuous. On I. Proof. So we write down the estimate which follows from the definition of Herder continuity. So now, if x1 minus x2 less than delta, then x1 minus x2 power m times less than m times delta power alpha, right? So it means if we want to have the estimate that it should be less than epsilon, not this one, no, that one, then what we need is, yeah, so in fact we can take delta equals to epsilon over m, right, power 1 over alpha. Once again, we don't know yet what it means, but that is a little bit early for exponent, right? That is positive number. That is a positive number, and okay, and in fact it proves everything, right? Because for arbitrary epsilon we can find such a positive delta such that for all x1, x2 which satisfy x1 minus x2 less than delta, we have also this inequality, and it gives the following estimate for the difference between f of x1 and f of x2. That's all. And now negative result. Negative result. Negative result. Theorem 2. If f is uniformly continuous on a bounded set x, then f is bounded on x. Proof. So suppose x is in an interval, right? Such an interval always exists since x is bounded. So then, okay, let me draw such a picture. We know that for arbitrary, I will not rewrite the definition, so let's choose epsilon, let's say put epsilon equals to 1, right? Then there exists delta greater than 0 such that for all x1, x2 in x which satisfy the inequality x1 minus x2 less than delta, we have an equality f of x1 minus f of x2 less than epsilon. No, epsilon is 1, less than 1. Let us choose, firstly, let us divide the interval AB, into, let's say, capital N intervals of, let's say, ij, of length less than delta. Let's say delta over 2, and that is doesn't matter how we divide it, equal or not, doesn't matter. So definitely we can do it. Then choose a point in ij intersected x, a point, let's say, xj, right? If ij intersected with x non-empty, right? J, okay, maybe I'll choose a point, let's say xj, like that. It's better to differ from those xj. J from 1 up to capital N. So we have finitely many points, xj's. I don't know, maybe less than capital N, because we are not sure that all of those sets are not empty. Then, now, for arbitrary x in x, there exists j from 1 up to capital N, right? Such that xj minus x less than delta, because, yeah, since those intervals cover the whole interval AB, they cover also our set capital X. So arbitrary point lies in one of those intervals for sure. Hence, we have a point xj such that this is true. Then f of xj minus f of x is less than 1 because of our choice of delta, or f of x is less than 1 plus modulo f of xj. So it means that f is bounded by so f of x is less or equal than capital M for capital M equals to maximum of modulo f of xj for j from 1 up to capital N plus 1. That is our capital M. So we have that the function f is indeed bound. Theorem 2, okay, I said this is a negative result. In fact, it looks like positive, but usually it is used in opposite direction. So if f is an unbounded on a bounded set, then f is not uniformly continuous. So let me give an example. Example of, I don't remember number, example 3, let's say. 1 over x is not uniformly continuous, on the interval 0, 1. Why? Because it is not bounded. So it follows immediately from Theorem 2, by Theorem 2. And maybe example 4, square root of x is uniformly continuous on 0, infinity. So here we cannot refer to Theorem 2, first of all because of opposite direction, right? But also we cannot apply Theorem 2 because this set is not bounded. Hence, square root of x is definitely not bounded, but it says nothing since the set also is unbounded. But what we can prove that square root of x is Hölder continuous, right? So square root of x1 minus square root of x2 we can write as square root of x1 plus square root of x2 over x1 minus x2, all right? And so oh, maybe let me take here from 1 to infinity, it's easier, right? Then what we can write, less or equal than modulo x1 minus x2 over 1. So yeah, less than, is it okay? Yeah, everything is okay. Less than epsilon if x1 minus x2 less than delta equals to epsilon, right? Yeah, that gives the result. So in fact, what we have proved is that square root of x in fact is Lipschitz continuous also, right? On this half line. Okay, let's stop for today. Thanks.